Hello students, my name is Shashank Shekhar and today is the fourth lecture of the chapter Biomolecule. So far we have started glucose and we have studied the chemical reaction and structure of glucose. Also we have seen the cyclic structure of glucose, that how some of the chemical properties of glucose cannot be explained using the open cyclic structure. Therefore we introduce a cyclic structure that was able to explain all of those phenomena that could not be explained with the help of your open chain structure. Clear? Also, we have seen the Haworth projection. So, today we will see more about the structure of glucose and then we will move to sucrose. Okay. So, if I talk about the syllabus here, so we have started carbohydrates now. We have studied the classifications on three different bases. The first one was reducing and non-reducing sugar. Second one was our number of carbon atoms. So, that is triose, tetrose, pentose, hexose. After that, on the basis of the position of the carbonyl center, that was named as aldose and ketose, and one more physical attribute that was considered was sweetness. So if it was sweet, it was considered as sugar, and it was not sweet, it was considered as non-sugar. Okay, so this was the classification. Then we have moved to monosaccharides. So what are monosaccharides? So monosaccharides are those saccharides which on hydrolysis, acidic hydrolysis I would say, gives no product at all, means they cannot be hydrolyzed further. So examples are glucose and fructose. Okay, then we have seen the DL configuration. I have made it clear. Now today we'll today we will see this fructose more. Okay, we'll see more about the glucose and also fructose. So let us start our today's class. So if I look at the detailed topic, first we will see what is chair form and what is Haworth projection. We will see you can say resemblance between both. Then we will see what is EP-mer and anomer. So although I have shown you what are anomers, I will today show you more about it. Then we will move to fructose, which is also a monosaccharide. So we will see structure of fructose and the cyclic structure of fructose. Then again we will see anomers of fructose. As we have seen the anomers of glucose, we will also see the anomers of fructose. Then the muta rotation and the osagon formation. So if I talk about the important topics of today, then I would suggest that you must know osagon formation and muta rotation. So these two things are important and they are quite technical to understand. So you should be conscious while looking at them. So let us start our today's class with say a resemblance of this chair and Haworth projection, comparison of this chair and Haworth projection. So this is the Haworth projection that we have seen yesterday. Okay, and I have tried to draw the chair form also, but it was not clear with the help of the board. So I put up a picture here so that you can get a more clear picture of the actual chair form. So this is the Haworth projection, and this is our chair form of cyclohexane. So what are these structures first of all? So this is alpha D glucose. Why is it alpha D glucose? Because OH is present on the downside at the first position. So it is alpha D glucose, or you can say alpha D glucopyranose. So because it is similar to pyrene, so it is pyranose. Next, we have drawn in analogy with this Haworth projection, I have drawn the chair form. How does it look like? So here is the chair form. You can see that this is the O that is here. At first position, the H is present on the upside. So, also it is not mentioned, although it is not mentioned here, but it is understood. So H is on the upper side. Okay. Then we have OH on the downside, then OH, then OH, then CH2OH. Yeah, this is up and this is down. So if you want to know more about the cyclohexane, then you must be aware about the chair conformation more. Okay. So one thing here is to mention is that, so if you don't know to draw it, so there are two positions, axial and equatorial, and up and down. So if we will have, if you remember this also, any position of any H atom in say I am remembering this one, that it is up, so it will be axial. So if I remember that at this position carbon, the up is axial and the down is equatorial, then further we can just follow this analogy. Now the up will go on opposite side, so you can see that initially it was present on axial position, this one. Now H will be present on equatorial and OH on the opposite side. Similarly for this position and similarly for this one and this one. Okay, done. Now we have placed the CH2OH group on the axial position. Why? So as to avoid 1,3 diaxial, sorry, in the equatorial position, so as to avoid 1,3 diaxial interaction. Okay, so this is the chair form of our alpha D glucose. Now I would like to draw your attention to anomeric effect. What is anomeric effect here? So if you just imagine this glucose here, let me draw it for you. So this is our anomeric effect. So I'm just drawing the oxygen first of all. Okay, oxygen first of all. Now oxygen will have lone pair. Of course, it will have lone pair. Now what will happen due to this lone pair? Lone pair will also be aligned in two ways, one axial and one equatorial. Okay, one axial and one equatorial. Now what will happen? So let me draw it for you in a page. So we have this here, oxygen here. Now since we have H here and OH here, and the lone pair will also be placed axially and equatorially. So this is axial and this is in the upside, and the downside we have equatorial lone pair. Okay, done. Now what will happen? There is an anti-bonding here of the OH bond, CO bond. There is a bond between C and O. There is a bonding. This is our anti-bonding. Suppose this is our anti-bonding. Anti-bonding. Okay. Now what will happen? And this OH, this O here, which has the lone pair, will donate its electron density to this anti-bonding. Okay, they will do interaction. So this interaction stabilizes this thing. Okay, so this interaction makes the structure stable. So this is called anomeric effect. So we will see more about an anomeric effect later on. This is the why it is called anomeric effect, because this is the anomer carbon. Here this is first carbon and it is anomer carbon. So it is called as anomeric effect as it is applied on the carbon that is present here. Now what is the result of this? What is the result of this? The result is the weakening of this bond, CO bond, because electron is going to the anti-bonding, and if a bond is receiving electron in the anti-bonding, that weakens the bond. Clear? So this was about the chair and Haworth projection. Now next is epimer and anomer. So I have tried to explain epimer and anomer again. So what is epimer and anomer? First of all, epimer. So epimer is generally the change of configuration of atoms in the spatial space at one carbon position. So suppose this is one structure and this is one structure. Okay, this is one structure and this is one. Now you can see here that this and this center have the same configuration. H is on the left, H is on the left, H is on the left, and H is on the left, while OH is on the opposite side for both of the carbons. But for this center, with both centers, we have OH on the opposite sides. So in this case, OH is on the right side, and in this case, OH is on the left side. So they both are epimers with respect to C2 carbon. Why C2? Because this is first, this is second. So they are epimer with respect to C2 carbon. Clear? Next thing, one more thing I forgot to tell you in the previous class. So if all the OH are present on the right side, if all the OH are present on the right side, then it is called as etheriose. And if it's all the hydroxyl group are present on the left side, then it is called as threose. So this is also a way of, say, optically defining a compound. Okay. Next one is anomer. So you can think of anomer just a subdivision of epimer. So anomer is nothing but the change of configuration, means the epimer with respect to C1. So you can see here at one position for C1 we have changed the position. Similarly here also, for whenever we will see the structure of fructose, there we will also see that we have changed the configuration at one position. So I have just put it for your reference. We will see more about fructose when we will study fructose. And for ketose, this C1 changes to C2. So this should be remembered. So we will talk about the anomers of ketose. We will see there also. Okay. Now let us start the fructose. So what is fructose? First of all. So first thing, fructose is also a hexose. Fructose is also a hexose, but a ketohexose. How is it so? We will see in the next slide. We will see the structure. How it is obtained? It is obtained along with glucose on the hydrolysis of cane sugar. So we have seen this thing. When we hydrolyze the cane sugar, we got glucose and fructose. And it is a natural monosaccharide found in fruits, honey, vegetables. In its pure form, it is used as sweetener. So this thing, that is the fructose, it is found in fruits and all. So it acts as a sweetener. It is sweet in taste, it is sugar. So it is also the formula of C6H12, but the structure is completely different. Okay, the connectivity is also different. Not only the spatial arrangement, but the connectivity is also different. Now let us look at the structure. So this is the structure of fructose. So first of all, as I have told you, it is the formula of C6H12. Again, we have first considered the open chain structure. We will consider the cyclic also. So this belongs to D series and it is levorotatory. Why D series? Because the OH is on the right side. This bottom OH is on the right side. For levorotatory, the bottom OH is on the left side. And next it is levorotatory, that means that it rotates the plane polarized light, the PPL, on the left side. So that is the reason for its levorotatory. And it is found to contain a ketonic functional group at carbon C2 and 6 carbons in a straight chain. So this is the structure. So we have 6 carbon, so it is hexose. Okay, this is hexose. And we have carbon I group at the second position. Therefore, it will be termed as ketohexose. Okay, clear? Now, next, let us talk about a cyclic structure of glucose. So again, we are not able to explain most of the properties of the say fructose with the help of the open chain structure. Therefore, we introduce the cyclic structure. Okay, cyclic structure. How does the cyclic structure look like? So we have a furan. Now, similar to glucose, as glucose was symbolic to the say pyranose, this fructose is symbolic to furan. So therefore, it is called as furanose. So it also exists in two cyclic form by the addition of OH at the C5 position. Okay. So this OH group again attack here at the say our ketonic group and makes this thing. So we at the second position, you can see here that the configuration has changed. Here the CH2H on the left side, here the CH2H is on the right side. Okay, clear? Got it? So this is called alpha D. This is called beta D. Again, alpha is for the OH on the right side and beta is for the OH on the, sorry, D is for the OH on the right side and alpha is for the OH on the right side of the C2 carbon and opposite it for beta. Now, this both of these structures shows a clear resemblance. We are not talking about the double bond, but it is similar to this furan. How it is a 5-membered ring: 1, 2, 3, 4, 5. Okay, so we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So 5 carbons are there. And it has also 5 carbon and 1 oxygen as the heteroatom in the chain, cyclic chain. Clear? Got it? Now, let us talk about the anomers of fructose. Anomers of fructose. So, as I have told you that in this case, not the C1 carbon, but the C2 carbon is seen. You can see here at the C2 carbon, the configuration has changed. So, if I want to generalize it, that how you will decide alpha and beta. So you have to decide it with the help of where the OH group has attacked. So if it is attacked on say C1, then we will see that one. If it has attacked on C2, then we will look at that carbon, that is the C2 carbon. So here the OH has attacked on the C2 carbon rather than the C1 because the group was ketonic. Okay, clear? Now if OH goes on the downside, again we have the alpha D glucose. The definition is same, no difference in that. If this OH group on the downside, then it is alpha. If it is the OH is going on the upside, it is beta. Okay, got it? So this was about fructose. Next, what is mutarotation? What is this mutarotation? So we know very well that there exists a equilibrium between this, and this. Now this equilibrium, since it is equilibrium, it will be true for all, no matter which form we are taking. So if we take alpha form, then it will just be opened and we move to this beta form. There will be some percentage of alpha, there will be some percentage of beta. So there always exists an equilibrium between these three structures. So this changing of say configuration of C2 carbon from alpha to beta is called as mutarotation. So it is basically the epimerization of a pure carbohydrate. So whether you take alpha pure alpha or whether you take pure beta carbohydrate, they will epimerize, means change the change the configuration of C at the second position, as we will add water, and it will happen until this equilibrium is reached, and this thing is called as mutarotation. This is called as mutarotation. Now how does this take place? So we have our say this glucose. Now what do? We add water on it. Now through reversible isomerization, it changes to your open chair form. So first it changes to open chair, and then further this open chair changes to beta, and this thing happen until the equilibrium value, until we have a rotation of plus 5 to 0.7 degree. Means the solution that you have taken will say epimerize, the glucose will epimerize until the rotation due to the solution is plus 5 to 0.7 degree on the means levorotatory by an angle of 52.7 degrees Celsius. Okay, got it? Now if I talk about how does this epimerization takes place. So this is the epimerization takes place. This is the epimerization of glucose. Remember that we are talking about mutarotation, and mutarotation is related to glucose. So how does this takes place? So let us try to draw the mechanism. So we have O here and OH here. Sorry. Then this OH is on the upside. This is on the upside. This is on the downside. And this we have the CH2OH. Now if we just put water in it, first of all what will happen? The H here will be protonated with the little amount of H plus that is be facilitated by water. Okay. Now what will happen? This will move here. This will move here. Okay, clear? Sorry, this will not happen. So this will move here. You will have a positive charge on this carbon. Okay. Now this will come here and create a negative charge. And this H will be taken from here. So we will finally move to this structure. So this is epimerization. So we epimerized from here to CHO, and then again the OH will attack and will form this opposite one. So in this way, whether you take any projection, whether you take any amount of say alpha D glucose or beta D glucose, it will be further epimerized such that your final rotation due to PPL is equals to plus 52.7 degrees Celsius. Plus 52.7 degree, not Celsius, sorry. Not Celsius, sorry for that. 52.7 degrees in the positive side, in the left side. Got it? Now, we have talked about muta rotation. Now you will see OSA zone formation. What you will see? OSA zone formation. So for OSA zone formation, this is the reaction that we have. This is the reaction that we have. So how would have this reaction taken place? So let us see it. So we have a carbonyl center here. O, OH, OH. H, OH. Okay, CH2OH, H, H, OH and H. Now first of all, this is the carbonyl center. NH2, NH2. And we have a benzene ring attached to this. We have a NH here. So this has lone pair. This will attack this center. What it will create? So we will have now N attached to this carbonyl center. Okay, and attached to this carbonyl center OH, O minus, sorry, positive on this H here, and rest I am saying it as R. Suppose NH2, and this is also as R. Okay, now there will be an interproton transfer. So suppose I am telling it with R dash. So interproton transfer takes place. This H will grow here. We will have N H now. We have H here, OH here, and R. Now further what will happen? This will go like this. And we will get our R dash N at the carbon center. So we have this N H, no H, sorry. Then we have phenyl. Okay. Then rest of this R. Now again we can have another same formation from this NOH. Okay. Clear? Now if you see both of this, if you see this and this, say they both are same at every stereochemical aspect except this center. Okay, so this has been changed. This has been changed to NNOH. So oxygen formation, what happens? It results in the loss of chirality center at C2 center, because now C2 is sp2 hybridized. sp2 hybridized is never optically active, so it does not affect other aryl center. So it is not affecting other chiral center. So this phenyl oxazone crystallizes readily under sugar and a useful derivative for identifying sugar. Now if you see this oxazone formation, then it can be used for the identification of the sugar, because it crystallizes easily, readily, unlike our normal sugars. Now how can we use it? If I ask you, how can we use it? Suppose we have two types of glucose. Okay, two types of glucose. Say we have one we can have, not two types of glucose, one glucose and one mannose. So what can be those? HHOH, okay, so this is glucose. If I ask you to draw mannose, so what is the structure of mannose? Do you remember? OH, H, O, okay, OH, H, O. Then we have OH, H, H, OH, H, OH. Now if I do the oxazone formation for this mannose, what will happen? What they both will give. So for oxazone formation, what do? We replace this thing, first of all this one, with N. Say I am writing it as pH, phenyl. Again this one is also changed to again. If I draw for mannose, what you will see? You will see that this will be kind of this. Yeah. Now if I compare the structure of the oxazone that has been formed for glucose and from mannose, they both are looking same. See, we have OH on the left, OH on the left, H on the left, H on the left, and with both H's on the left. Means all of these were same initially. The only difference between the glucose and mannose was this carbon center. Now this has been changed to the oxazone here with a double bond N, and it does not have any such compulsions. Therefore, they both will have the same structure. Means they both will give the same osazone. Now, if I ask you, can you give me more examples of carbohydrates having the same osazone? So we can name a number of them. So starting from allose and ultrose. First, this one, they both give the same osazone. Then we have galactose and malose. Third, we have glucose and indose. Fourth, we have our glucose. Sorry, this was glucose, I think. Yeah, this is glucose. And this is mannose. This is galactose. Galactose and mannose. Got it? Similarly, we can have indose and this can be gallose. So all of this have the same osazone formation. Means the two carbohydrates which have only different configuration at the C2 carbon, which have the different configuration at the C2 carbon, and rest of the carbons are having the same configuration, will give the same osazone. Okay, clear? Because in osazone we change the configuration of the second carbon to C double bond N. Got it? Now next I will give you again the chart that we have seen yesterday, so that you can get the more clear picture what I told you right now. So here is the slide that we have seen yesterday. So if I consider the osazone formation, so ribose and arabinose will give the same, because we will have our osazone formation is this carbon and this carbon. Similarly, xylose and lexose will have the same. Again, our allose and ultrose will have the same. Then glucose and mannose will have same. Then glucose and idose, and then galactose and tallose. Okay, so just these two pairs, if you consider these two pairs, so these two pairs will have the same osazone formation. Okay, clear? So what we have studied today? So far. So first we have seen the cyclic structure, that is a chair form of our glucose. So what does the chair form looks like? Okay, chair form looks like. So we have seen it, and we have seen that the chair form was a much appropriate presentation of how does the glucose exist. Then we have seen fructose. So fructose was a ketohexose. Okay, ketohexose. Then we have seen some properties of ketohexose and the structure that it is resembled to our say furor. So it is called furanose. Then we have seen what is enomer and epimer. Okay, then we have seen what is enomer and epimer. So epimer is basically the change of configuration at one point. It is a change of configuration at one point, whether C1, C2, C3, or I would say change of position, not change of configuration at one point of an optically active center at one point is called as is termed as epimer. Now if the epimerization is taking place at the C2 carbon, then it is called as enomer. Now after that we have seen mutarotation. So mutarotation is basically the epimerization at C1 position, because there exists an equilibrium between the three structure, that is the open chain structure, the cyclic structure, that is the alpha D glucose and the beta D glucose. So there exists equilibrium between these three. Got it? And this equilibrium is more shifted toward that which is having CH2OH on the upside. Okay, there is less 1,3 diaxial interaction. So I have told you that which one is more stable. You can just go and see to it. Then we have seen that this if whether we take any PO form, whether we take alpha or whether we take beta, this will finally epimerize and form the solution such that upon addition of water, I would say, upon the addition of water, this will epimerize and form the equilibrium, or the equilibrium will be existed in such a way that the rotation is plus 52.7 degrees. Okay. At last, we have seen what is OSA zone formation. So it was basically the reaction of the carbonyl center with this carbonyl center with our OSA zone. So OSA zone was looking like this, which was NH2, NH, and phenyl. So I have not told you one of the reaction of the OSA zone formation. So let me give it for you. So one was the nucleophilic substitution. So I have shown for the first carbon only. So let us do it for the second carbon. So how does the second carbon does this? Because it has an OH group. Okay, it has an OH group. So how does it happen? So let us say it. So first let us draw the structure of our glucose. The structure looks like this. So we have done the OSA zone formation at first position. So we'll write it in this way only. So we have phenyl here. Okay, we have phenyl here. But we have an OH here. We have an OH here. So how will this reaction take place? So next what will happen? So I am writing it as R. Okay. This will go here. There will be an interproton transfer. Interproton transfer will take place. There will be a double bond and N negative charge. H will come here. Okay, so I am H here. Now this is a acetal. Sorry, this is a ketone. Okay, so this will enol. Sorry, this is enol. Sorry for the confusion. It is enol. Now this will convert it into C. It will remain as it is. NH, NH, PH, and C double bond O. Okay, clear? Now next what will happen? So again we have a carbonyl center. Again we have a carbonyl center. This will be again attacked by the NH, NHOH, NH, NH2. So this is NH2, NH, PH, and this will again replace this. So we already have a H here. Sorry for that. Yeah, we have a H here. And as it will form, this will result in CH2. So we have CH2, CO. Now this thing will be converted back to CHNH. And upon attack of this here, this will again give N, NH, PH. So in this way, the OSA zone formation takes place. And what are the species that give the same OSA zone formation? So we have to just look at the pairs that are derived from the top one. So ribose and arabinose will give the same OSA zone, and the xylose and lixose will give the same. Similarly, the allose and ultrose will give the same OSA zone. Glucose and mannose will give the same OSA zone. And your glucose and idose and the galactose and tylose. So all this pairs in the boxes will give the same osazone. So this and this will give same osazone. This and this will give same osazone. This and this will give the same. This and this. This one and this one and this one and this one. Got it? So you can do the mechanism by yourself. Each of these will have the same mechanism which I have told you earlier. So you must try to do it by yourself. That would make your life easier. So this was for today's class. So we have covered glucose and fructose whole. So today we will start with disaccharides. So we are done with the monosaccharides, the glucose and fructose. Tomorrow we will start with the disaccharides. So with this, I end my lecture. Thank you.